I'm going to give a quick reminder here about what a slope field is, right? So a slope field is just a bunch of little lines, right, that represent the slope of the line tangent to y, right? This is the slope tangent to y. And when we solve a differential equation, what we're looking for is the functions y that satisfy this differential equation. So the slopes of the line tangent to y are what we're sketching. If we do enough of them on a small enough scale, the idea of linearization, that the derivative resembles the function on a small scale, should tell us that we have a pretty good picture of what the solution to this differential equation is. And this differential equation right here is one that you guys are not going to be able to integrate on your own this year. If we were in Calc 2, we'd have a method for this, but we don't in Calc 1. So that's the idea of what these differential equations are. So what we do is we look and say, all right, all I have over here is x's. And so I say, if x equals 0, that's an easy value to plug in. What is dy dx end up equaling?
One.
So anywhere where x is 0, which is along the y-axis, I draw little lines that have a slope of 1. What about if x is 1? What do we get for dy dx?
1.
We'll get 1. In a minute, we're going to take a look and see what's happening between 0 and 1, just to have a sort of an idea. But for now, we'll just move up to 2. What happens when x is 2?
Root 3.
Get root 3. Right? No, root 3 is a little more than 1, right? So a little bit steeper. So all of these lines should be just a bit steeper than a slope of 1. What about when x is 3? What happens? Should get root 7, I believe. Yeah. Which is even steeper, right? So as we continue, and if we continue out to the right, what's going to continue to happen to each of these? If I plug in 4, right, that's going to be root 13. If I plug in 5, that's going to be root 21, and so on. These are just going to keep getting steeper and steeper and steeper as we move to the right. Would you all agree with that?
Yeah.
Okay. Great. All right. What about if we go the other direction? For example, with x equaling -1, what would dy dx be? That should be 1 minus -1 plus 1 root what?
3.
Root 3. So back to the same as this one where they were x equals 2. So a little steeper than 1. And if we continue moving to the left, when x is -2, what does dy dx equal? Should be root -2 squared is 4, minus -2 is 6, plus the 1 is 7, so root 7. So getting still steeper, right? And if we were to continue to the left with -3, we'd note that this is going to just become root what? Becomes root 13, and then it's just going to keep getting larger and larger and larger. These are just going to keep getting steeper and steeper. Everybody agree with that?
Yeah.
Okay. And now we noted that we had 2 columns in a row that were exactly the same. So when that happens, you might be interested in what's happening in between there. Usually on the AP test, they just tell you a bunch of points to do. They don't just say sketch the slope field and just give you a blank graph. They'll usually put a bunch of dots in and say sketch it at these specific points. But just for fun, let's see what's happening if x is, let's say, a half. A half squared is 1/4, right? Minus a half is -1/4, plus 1 is 3/4, and the square root of 3/4 is root 3 over 2. And root 3 over 2 is a little bit less than 1. So like it should be flattening out just slightly in between there, right? Not too much, but a little less than 1, anywhere in between those. So if I were to try and sketch the solution that went through the origin, it should be at a slope of 1. It should get a little less and then back up to a slope of 1 and then get a lot steeper and get steeper here as well. Good or no? And a similar thing might happen if I tried to sketch one that went through, let's say, this point. It'd start like this, get a little steeper, and then it'd go to 1 and get a little less steep. And we just have these little sort of bumps in the curve. We could sketch the curve through any point in the plane using our slope field. Good or no?
Good.
Cool. So the first two we did, the cosine x and this x squared, root x squared minus x plus 1, were fairly straightforward because I just needed to plug in an x value, and no matter what the y value was, all the x values, or all the lines on that same x value were all the same because there was no y over here. But now we're going to move into some differential equations that include both an x and a y value. Okay, so both an x and a y. And so now the point at 0, 0 and the point at 0, 1 will be very different from each other, right? Because 0, 0, and 0, 1, even though the x value is the same, the y value changes, and the y value is now part of what we're looking at here. So we're going to try to do this with, and this is sort of what they'll normally do on the AP test, like I was saying. They'll give you a set of specific points to do this at. So I'm going to say, let's sketch the slope field at those given points. So I got 25 points there to sketch that. And we're going to find a way to make it easy that we don't have to just plug in each individual. And you could plug in each individual set of points and figure out exactly what each one is, but there is an easier way to do this. So anytime you have x and y as part of your differential equation, and there's a plus or a minus in between them, as opposed to multiplying or dividing the x's and y's together, what you want to do is you want to set dy dx equal to some specific value. So what's a nice easy value to start with?
0.
0 is, exactly. So if dy dx equals 0, that means that x minus y equals 0, or that y equals what?
X.
Exactly. Which tells us that whenever y equals x, the slope should be 0. So anywhere along the line y equals x, the slope should be 0. So these are all the points where y equals x: 0, 0, 1, 1, 2, 2, negative 1, negative 1, negative 2, negative 2. All of those are where y equals x. They all have a slope of 0. Make sense?
Yeah.
All right. What about when dy dx equals 1? What does y equal?
X plus 1.
I think it's x minus 1, yeah? If x minus y equals 1, bring the y over and subtract the 1. We get y equals x minus 1. So anywhere along this line, the slopes are all 1. Everybody agree with that? Or no?
Yeah.
Okay. What about when dy dx equals 2? What would y
What?
equal?
X minus 2.
Okay. So that'd be down, well, that was way too steep. That'd be down here. And what about when dy dx equals 3? It's going to be down here, a little bit steeper, and down here a little bit steeper. Oh, last two weren't very good. just going to keep getting steeper as we follow these lines this direction. Everybody agree with that?
Yeah.
All right, and what about if we go with negative values? dy dx equals -1. That ought to give us y equals what?
X plus 1.
Okay. So along that line, we need slopes that are -1. And then the next one up is probably going to be -2. We could plug those in and see that. And then -3 and -4. And we end up with something that looks, kind of like this. And let's see if I can get my toolbar here to do a couple different colors in here. Half the time it doesn't show up though when I try to open it. Yeah, like right now it doesn't open. Okay. So let's suppose we wanted to sketch the one that went through this point 0, 1. Well, it should be at a slope of 1, and it should be increasing and getting steeper, and then it should be decreasing to 0 and increasing up to 1. We should get some function that looks like that. Good or no?
Good.
Or what if we picked some point down here like this one? It would be decreasing that slope up to 1. And if the slopes are 1 along a line that has a slope of 1, that sort of gives us this little oblique asymptote here that we might have. So we might have down here, if we picked this point, we might get something that looks like this, but up here we'd get something that looks like this. And it just sort of depends which point you're choosing to go through. So I might give you an initial condition, say you're like, sketch the one that goes to the point 0, 1, you'd sketch this one. Sketch the one that goes to the point 1, -1, you'd draw something that looks like that. Does that make sense? Any questions on that? Or is that okay with everyone?
What does the slope field represent?
The slope field represents the solution to this differential equation. It represents the equation that solves dy dx equals x minus y.
Do we have the equation of the slope field itself?
There is no equation of a slope field. The slope field is derived from your differential equation. It's a graphical representation of what does solve this, but we can't. This specific differential equation is one that we are not able to solve. So we're not going to be able to get an explicitly defined function that has this as its derivative. And it's not something we'll be able to do in this class. But this is a graphical representation of what the solution to this does look like, to the function that has x minus y as its derivative.
Got it.
So yeah, the point of it is, all right, we can't anti-differentiate this, we can't find the solution to this, but we can have an idea of what it looks like because we can use the idea of a derivative and linearization to sketch its solution using the slope field. Does that make sense?
Yeah.
So with this specific graph, like each point, or like if you were to start the line at like each different point, there would be a different line like every single time.
It would look a little bit different.
Or-
Yeah, so suppose we picked this one up here. Right here, let's say. Well, it'd be getting steeper even more quickly, and it would be flattening out eventually, and still, actually, it'd probably, since this is a steeper line, it'd be coming down here and then getting something like that. It'd still be approaching that asymptote down there. But yeah, they'd look, everything above this line would look pretty similar. They'd all sort of have this same little scooping little action to it. It gets super steep as you go to the left and approach this line as you go to the right. Everything down here would sort of curve like this one does, just based on what the slopes look like. But yeah, every single one will be different, but there's a pattern for them. Because remember, each of those just represents a different constant within the solution to this differential equation. So like if I said, the initial value was x equals 0, y equals 1, we'd get this one. But if I said x equals 0, y equals 0, we'd end up with one that was, down here going up and then get steep like this. So they look similar, but not exactly the same. And if we had the solution to this differential equation, we would then know. And in the next one, I'm going to be able to, we're going to work a little bit more with the next one, and we'll be able to actually find the function, because it's not similar to this. It has x and y, but we'll be able to solve it. We'll be able to see that depending on what that plus c value that you get is from the solution to it, you'll get something, you'll get to see different versions of what it might look like depending on the c value that you plug in. Does that make sense?
Somewhat, yeah.
I think it'll make more sense after we do the second one, but for now, is this good? Everybody good with like how we got the slope field and sketching a couple of the different solution curves that go through it? All right, so let's take a look at this next one, and I'm going to say, oh, shoot. Now I've messed this up. Give me 1 second here. All right, so I want you to do this at all of these points. And you'll note that I'm not going to have you do it at the origin. Why won't I have you do it at the origin?
Undefined.
Yeah, it's well, not that it's undefined, but that it is indeterminate. Oh, wow, I told you guys 3 in each direction, huh? That's a lot. I should have just had you do 2 in each direction. Oh well. All right, so these are the points that we're going to look for our slope field for. So the first thing that I would normally do on any that are a product or a quotient of x's and y's is figure out what makes it 0 and what makes it undefined. So it should be 0 if x is 0. So x is 0 should be 0. But y not equaling 0, which is why we're not at the origin. And it should be undefined or vertical whenever y is 0, but x is not 0. Everybody good with those first 12? Or no?
Yeah.
Okay. So then I would just look at a nice easy point like x equals 1, y equals 1, right? 1 is going to give me a half. So the slope of a half. And then I'll look at what happens as I go to the right from 1/2. So if I plug in 2, 1, should give me 1. So it's going to get steeper. And then if I plug in 3, 1, it should continue to get steeper, right? And so the same thing will happen. If I find this one, it should continue to get steeper. And if I find this one, it should continue to get steeper as I go out to the right. Okay. So then we'll look at what happens at 1, 2. At 1, 2, it should be what? Should be a 4th. So even less steep, but then it's going to get steeper and steeper as we go. And we'll note that as we continue up, as the y values get larger, but the x values stay the same, it becomes less and less steep, but they still increase as you go out to the right. Everybody good with that? Everybody see that?
Yeah.
All right. Now what's going to happen if I flip one of the signs here? Let's say we make x negative. Should be exactly the same, except negative values over here in the second quadrant. And so we should note that this pattern should relatively sort of repeat itself as we go through. And if we just make the y's negative, it should still be the same, except it's just going to flip the sign. So instead of having a positive a half, we'll have a negative a half, and then a negative 1, and then, and so on. And so same with these, we had negatives here, so these ones should be positives. And it should just repeat itself as we go through. So figuring out the next ones should be Once you get one quadrant done for these, should be pretty easy to get the rest of the quadrants. Everybody good with that? Yes, no, maybe.
Yeah.
Wonderful. So suppose I asked you to sketch the solution that went through the point 0, 2. Well, it should be flat-ish and slowly start to curve up, right? On both sides. If I asked you to do one down here, same thing, except it's going to curve down. If I asked you to do one over here, like let's say this point, it's going to curve up like this and down like this. But the thing about these solutions to differential equations is we always want them to be a function. And if I were to continue like this, it's no longer a function. True? Doesn't pass the vertical line test.
Yeah.
So we have to stop and make my solution curve a function. Your solution curve has to be a function. If your solution curve is not a function, you will get it wrong. So stop here, make it a function. Don't curve down and let the vertical line test be failed. Good or no?
So just with the, just helping me to get like a conceptual understanding. So those lines are the solution to the differential equation at that point?
Correct.
Is that right?
That is 100% correct. Or very good approximation of it.
Okay.
Yep. Okay. Any other questions on how we construct the slope field and what it is before we transition into how to actually solve this differential equation, because we will be able to solve this. And in fact, we're going to right now, if there's no questions. All right. We've got dy dx. What was it? X over 2y. Is that right?
Yeah.
All right. So anytime your differential equation has x and y in it, and you can write x and y as some sort of function in terms of x, either times or divided by some function of y, then you should be able to find the solution. And I'm going to have this written on a page in a minute here also, but we call this a separable differential equation. And we should be able to solve explicitly for y by separating the variables. That's why they call it a separable differential equation. So all we need to do is get the 2y to this side and the dx to this side, which we should be able to do. If I multiply both sides by 2y, I will clear it off this side and I'll have it on this side, right? We'll get 2y dy. Do you all agree with that?
Yep.
And on this side, if I multiply the x by dx, I'll get x dx. And on this side, the dx goes away. And so now all we need to do is just integrate both sides. What's the integral of 2y dy?
Y squared plus c.
Y squared plus a constant. And what about over here? X squared over 2 plus some other constant. Now, important point to note here that we'll talk again about, I'll mention a few times probably, is that when I integrate the left, I get a constant. When I integrate the right, I get a constant. These constants may or may not be the same, right? It doesn't really matter. But normally we don't write the constant on the left-hand side with the y. We'll only put one on the side with the x. Why is that? Well, because I could write it like this: y squared equals x squared over 2 plus c2 minus c1. Right? And what's c2 minus c1?
A constant.
It's just some constant, right? And all we're going to eventually do is find a constant if we have an initial condition, which we don't in this one. So normally we only put the constant on the side with the x. So we'll end up, and I'm going to give us another new page here just so that I don't cram it in there at the bottom. Y squared equals x squared over 2 plus some constant. And what does that give us? It gives us y equals the positive or negative square root of x squared over 2 plus c. Good or no?
So that's like the equation to the graph that we were sketching in the previous problem.
That's exactly correct. And so what we are going to do real quickly now is look at that on Desmos. Yes, can you guys all see Desmos now?
Yeah.
So x squared over 2 plus, I don't know, some constant. I'll just put in 2 there. That sure does look like exactly what we, I mean, not exactly, but it looks generally like what we sketched, doesn't it?
Yeah.
Yeah. If I put in a plus 3, it just moves it up a little bit further, right? If I put the negative sign out in front of it, we get the piece down here below on the bottom. Okay. And what about the pieces over there on the sides, like, you know, way out here that we had some, we sketched one, in fact, that was way out here, right? Well, where does that, where is that? I don't see any. I mean, I can't imagine putting in, you know, -3. Oh, there we go. See, put in our -3 and we end up with these ones, right? So negative constants are going to give these ones out here. And I can make this positive and we get the ones up here. Good or no?
Can you go back to when you showed the work, the first page of it?
Sure. We're going to do a bunch more of these here in just a minute. Was that conceptually, does that make sense to everybody? And we see how it's related to the graphs that we sketched on our slope field.
In the differential equation here, it's just is it just the integral of the right side of the equation, or is there like, am I missing something else there to the concept of a differential equation? Or
Well, we have to integrate both sides of it, which we normally did, right? In the past, we just had a dy over here and we integrated that to get y equals something. Well, now we have some function in terms of y over here. So rather than just getting y equals, we have to integrate that and we end up with y squared equals something. And so then we have to solve for y.
so it's like the integral of both sides and then you solve for y.
Exactly. That's the only thing we're adding to it, is that if it's a function of x and y on the right-hand side to begin with for a differential equation, where they're being, you know, multiplied or divided by each other in some way, we separate the variables and we integrate both sides. Does that make sense?
Yeah.
Cool. Anybody have any questions on that? So there's the ending of it there if you still needed to get that down. All right, everybody's good, no questions? So this is sort of the written out explanation of what we just did. So it's a differential equation of the form dy dx equals a function in terms of y times, or it could be divided by a function in terms of x. We call those separable, and we rewrite the variables with the function with y on the left, the function with x on the right, and we get the dy on the left and the dx on the right. And then, like we just did, we anti-differentiate both sides and solve for y. And so we'll be able to do this with any, like I said, any function that's a function of x times y, or x divided by y, or y divided by x. And we'll even now be able to throw in initial conditions to it and be able to find the specific solution to a separable differential equation given some point that we want it to go through. So that's going to be our goal here for the rest of class today and a little bit of Monday, is to solve these separable differential equations. And it's also what your homework's going to be on. Exciting. I'll give you guys a second to get that down if you want to write that down, and then we'll work through a few of these. All right. So here we've got dy dx equals x times y squared. And we've got y equals 1 when x equals 1. So we'll note that it is a product of x and y. In fact, it's, if we wanted to rewrite this by applying that square to both terms, we have this, right? It's a function in terms of x times a function in terms of y. And so in order to solve this separable differential equation, what we want to do is separate the variables. So the x squared will stay on the right, and we'll bring the dx over there. And the y squared will move to the left-hand side. So we have to divide by y squared. So we'll have dy over y squared. Good or no?
Yeah.
All right. So immediately, now that we have our variables separated, we will integrate both sides. And the right-hand side is nice and easy. That's x cubed over 3. And we're going to put our constant over there with the x's. So x cubed over 3 plus c. And over here, the integral of dy over y squared. Well, at this point, I hope you aren't making this mistake, but a lot of people are still. This is not this. Right, this is the integral of y to the -2. You can only do that if it's a single variable down there that's not a function. If it was dy over y, sure, natural log absolute value y. But it's y squared, which is y to the -2, which means we're going to integrate that, which means we'll go up to -1 and divide by -1. So we get negative y to the -1. Right? And if I wanted to, we could write that as -1 over y, which is probably a little nicer way to write it. Everybody okay with the integration there?
Yeah.
Okay.
Yep.
So there are some teachers that will tell you to solve for y now and then evaluate to find your constant, but I am not one of them. I think it's much easier if you immediately plug in your initial condition to find your constant right away. So if y is 1, we have -1. And if x is 1, we have 1/3 plus c. And what do we get for our constant?
-4/3.
-4/3. And so now what we're looking at is -1 over y equals x cubed over 3. There was a -4/3, right? Minus.
Yeah.
Yeah.
And now we'll solve this for y. So first off, we could combine this to become x cubed minus 4 all over 3. And if we divide that by a negative, we've just got 1 over y equals x cubed minus 4 over 3 with a negative sign out in front of it. And then we just need to take a reciprocal. Y equals 3, or negative 3, over x cubed minus 4. And couple of things. One, you cannot take the reciprocal unless these have a common denominator. So if this was x cubed over 3 minus, 2/5, you can't just take the reciprocal of both fractions. A lot of people try to do that last quarter and over the past few years as I've taught this class. You have to get a common denominator and combine them together as one fraction first. And make sure you do that. Then you can take your reciprocal. Now we're not quite done here. And why are we not quite done?
Is it because there's like an x in the denominator, so it can be undefined at like some
Exactly.
value?
We still have to find the domain restrictions and state an interval of validity. So we know that x cubed minus 4 cannot be 0, right? Because that would mean we're dividing by 0. That means that x cubed can't be 4, or x cannot be the cube root of 4, which tells us the domain is negative infinity to negative cube root of 4 union cube root of 4 to infinity. But we don't put both of them. We only put the one piece of it that includes our initial condition. So our initial condition was that x equals 1. Well, I'm sorry, this is both. I don't know why I put a negative cube root of 4. That's cube root of 4. Our initial condition is that x equals 1. So we're going negative infinity to cube root of 4 or cube root of 4 to infinity. Which one of those includes x equals 1?
Negative infinity to cube root 4?
Exactly, just this one. So this one we won't include. This is only valid, or only has to be this function for negative infinity to the cube root of 4. Good or no? All right, yeah. A couple people want me to go back to the last slide. Any questions on that while people are finishing copying that down?
What's the reason again that we only want one, like, set for the domain?
So it's just a technical thing that we do. It's called the interval of validity, and the reason we only choose the one piece is because we could have any constant on any of the other pieces, on any of the other continuous sections of it, but we have to specifically have a constant of negative 4/3 between negative infinity and the cube root of 4. Otherwise, that part of it doesn't have to go through this point. Past cube root of 4, I could have any constant I want. I could add 1,000 to this, right? And the derivative would still come out to be this. And it would still, because we had to have a constant of negative 4/3 for the other piece of it, it would still go through that initial condition. Does that make sense?
Oh, okay.
Yeah.
Yeah. Got it.
Any other questions there? Okay, let's do another one. So what are we going to do to separate our variables here.
Just cross multiply.
Okay, so we should end up with what? dy over y equals dx over x. Good or no? Hopefully good. All right, and then we'll integrate. What do we get on the left?
Natural log of the absolute value of y.
Equal, oh, sorry, I wrote an x there, of y. And it should equal what? Natural log of the absolute value of x plus some constant. So now two things we need to do here. Immediately we look at this and say, all right, this is the equation with our plus c. There are some restrictions already on what x could be, right? X cannot be what?
Zero.
0. So we need to keep that in the back of our minds as we're going through and doing our interval of validity later on, because this may disappear at some point. We may not have this natural log anymore, but as soon as we integrated, we had a restriction on the equation that we got. And just because if we simplify for y, that restriction disappears, doesn't mean we can ignore the fact that it did have that restriction. Okay, so always check if there are any restrictions on your x values immediately after you integrate and as you go through to the end. Okay. So we'll plug in our initial condition. Natural log 2 equals natural log 2 plus a constant. So our constant should be 0. And now we just have natural log absolute value y equals natural log absolute value x. And what do we end up with then?
X equals y.
Yeah, and how do we get that? We have to exponentiate this technically, right? And that gives us absolute value y equals absolute value x. And then we'd end up, clearing off the absolute value by saying that y would have to be positive or negative x. But we only pick the one that makes sense for our initial condition. Okay. And so if x is 2, y needs to be 2. So because of that initial condition, we will say that y equals x. And we will state that this is only for 0 to infinity, even though the domain of this is all real numbers. We had the restriction that x couldn't be 0 from the beginning. And so that would have made the domain negative infinity to 0, 0 to infinity, and we pick the one that includes x equals 2. Good or no?
So we always have to be looking out for domain restrictions throughout the entire problem. We can't just wait till the end.
Correct. Because sometimes those domain restrictions are gone by the time you've explicitly solved for y. But this technically is the, well, with the plus c, this is the equation that we get from this. And then we simplify it down to be something that's a function that we are used to looking at. But we have to take into account every step along the way.
Okay.
Do you ever need to think about the domain in the original equation before you integrate it?
That should give you a clue as to what your restrictions might be. At least it could potentially give you a clue towards it, but you don't need to specifically look at it. So if we looked at that one, right, x couldn't be 0, but that might not tell us, that might not necessarily tell us that that was a place where our integral might not equal 0, because our integral could have, the derivative just represents, the derivative being undefined represents 4 different things, right? It could be a vertical tangent line, it could be a corner, it could be a cusp, or it could be a discontinuity. And so for this particular one, it became a discontinuity. But it could be a corner, it could be a cusp, and it could be a vertical tangent line, in which case the function itself would still be continuous at those points. So it gives you an idea of what your restriction might be, but it doesn't guarantee that that's a restriction on the original function. Does that make sense?
Yeah.
Okay, cool. Any other questions on that one?
Is this the opposite of implicit differentiation?
Yeah, in a way, sort of it is, yeah. Yeah. Working backwards from multiple variables to the original function. It's not exactly implicit differentiation in reverse, but it's sort of, it's an okay way to look at it.
So if you were to implicitly differentiate y equals x, you could get dy over dx equals y over x?
Yes, you should. Yep. I mean, if you take, well, I mean, just if you take the derivative of y equals x, right? What do you get? You get dy dx equals 1, right? Well, let me give us another page here. If if y equals x, then dy dx equals 1. True? But we started with y equals x, and we also started with dy dx equals y over x. Well, if y equals x and dy dx is y over x, then we could rewrite this as y over y, which is 1, or we could rewrite it as x over x, which is 1. Does that make sense?
Yeah.
Yeah, same thing with that first one we did way back here. What did we get as our original, our final function? We got -3 over x cubed minus 4. So if we were to differentiate -3, in fact, let's just for fun do that. If y equals -3 over x cubed minus 4, then we should get, what do we get if we take that derivative? This is the reciprocal rule, so dy dx should be the opposite, so the negative will cancel out. The 3 will still be there. We multiply by the derivative of the denominator over the denominator squared. And so we started with dy dx equals x squared, y squared, right? Or x times y squared. Well, x squared would be what? Just x squared. There's my x squared. And y squared, well, y was this, -3 over x cubed minus 4. Squared would be 9 over x cubed minus 4 squared. And there's your 3 times 3, which is 9 over x cubed minus 4 squared. Does that make sense?
Yeah.
Yeah. It's kind of cool, I think. All right, let's do this one. It's probably the last one that we do today. And then we'll save a couple more for Monday. So let's separate the variables here. We got dy dx equals y plus 5 times x plus 2. Should give us dy over y plus 5 equals x plus 2 dx. Good or no?
Good.
Okay. On the right-hand side, what does that give us? X squared over 2 plus 2x plus a constant when we integrate. And then on the left, this one we have to do a simple u sub for it, right? Dy over y plus 5, we'll have to let u equal y plus 5 because it's a function in the denominator there. Du becomes dy. So this becomes an integral of, well, it just becomes an integral of du over u, which should be natural log absolute value of u. And I'm just going to put in the y plus 5. So that one does come out nicely as just a natural log absolute value of that function. Everybody good with that or no?
Yeah, good.
Okay, plug in 1 for y, gives us natural log 6, Plug in 0 for x, gives us 0 plus 0 plus c. So our constant is ln6. And we'll note that right off the bat, x squared over 2 plus 2x plus c, no restrictions on the values of x. We don't care about restrictions on the values of y because we're solving for y in terms of x. We're determine if it's a function in terms of x. Okay. So on the next page, we'll say we've now got natural log absolute value y plus 5 equals x squared over 2 plus 2x plus natural log 6. And how do we go about solving for y in this case?
Would you have to exponentiate both sides?
Exactly. We'll make both sides as a power of e, gives us absolute value y plus 5 equals, and then anytime I have e to some power of a bunch of things being added together, what you want to do is you want to take the ones that are, you know, the x squareds and the x's and anything that doesn't have a natural log with it, and put it as 1e to a power, and then multiply that by the other one, right? Because if you think about exponent rules, right, x to the a plus b plus c could be rewritten as x to the a plus b times x to the c. Isn't that like one of your basic exponent rules from
Yeah,
grade or
power.
something?
Yeah.
So we could rewrite it like that. And the reason why we want to do that is because e to the natural log 6 is just what?
6.
6.
6. So we can put that coefficient of 6 out in front. 6e to the x squared over 2 plus 2x. And how do I clear off the absolute value? What do I need to do to the right-hand side?
Would you like negative, positive, negative? Is that what you did? Or?
Positive or negative, exactly. And we can't have both the positive and the negative for our final answer. We'll have to choose one of these. And how will we choose? Based on,
The values given.
right, based on our initial condition. Okay, so we end up with y equals -5 plus or minus 6e to the x squared over 2 plus 2x. Our initial condition was when y was 1, x was 0. So if I put in 0 for x and 1 for y, do I need the plus or the minus in here?
Oh, the plus.
The plus, right? If I had a minus, I'm going to get -5 minus 6 because e to the 0 becomes 1. So -5 minus 6 will be -11, but the -5 plus 6 gives you the 1 that you need. So we pick the plus. And our solution is y equals -5 plus 6e to the x squared over 2 plus 2x. And we can plug any number in for x, square it, divide it by 2, add 2x to it. We can take e to any power, multiply that number by 6. You could do -5 plus any number. And there were no restrictions as we went through on the x values. So it looks like this is good for negative infinity to infinity. Good or no? Any
Good.
questions there?
Oh, because you plugged in 0 to get to get it to equal 1.
Right, if I plug in x equals 0, right, this becomes e to the 0, which is 1, and then I have 6 times 1 here. That's why I had to choose the plus instead of the minus, because -5 minus 6 doesn't give me 1. -5 plus 6 does.
Oh, okay, cool.
Any other questions?